So real analytic chains, and it has a very precise meaning in geometric measure theory that I will not go in details, satisfying some properties that there are integral currents that are locally integral currents that live here in the product, but such that when I look at the projection, so this has a projection in V, and there's a projection in W, let's call this spice of V, this is spice of W, that phi sub V, which is treated as support of the current T, is proper, that as a finite fibers, so intersection of the support of the current is less than infinity, and the third is that the boundary of this current is zero, so the closed currents that live in there. And so the idea, you can see something like this. So this is V, and this is W, so this is V cross W. So this can be seen as the classical picture that you would have, but probably this will extend beyond this so that it has no boundary. And it maps finite to 1 in the proper fashion and is onto, so this is proper and surjective. And the idea is that, and I'll make a precise statement, is that if I pick a point here, X, I can, well, suppose that two of these sheets meet here. There is a way in geometric measure theory, in the same way that there is in algebraic geometry to do intersection when things intersect properly, I can attach weights to these points in the fiber intersecting the support of my current, in such a way that it's a proposition here. It's called the slicing process. A proposition is that if I have something that lives in this world, then number one, they slice in the sense of currents, which is now a zero current in this, exists for all x in V, and this is called the slice. Basically is look at the fiber with the proper number of multiplicities, but what's nice about these also is that the function, the map, now from V to, let's say, to the zero currents on W, that sends X. Now remember that this is a zero current in the product, and I have to project down to W. When I project it down, under the other projection, the slice is continuous. So remember that the zero currents is essentially the same as the space that I call Z of W, or the free abelian group on W with a certain topology, or at least there's a map. One is the one compactly generated topology on the other, but and that answers one of the questions: how to create maps from something into space of this type. This is a way. But now, what I'm going to do is I will show that there is a composition map between those things. But before I go on, I would just like to make an extension. This is a remark. We will enlarge, I want to have a slightly larger category, enlarge the analytic manifolds to include analytic manifolds with corner. Okay, there is a notion of manifolds with corner, and that's what they look like. They have a corner, but they're still analytic, and so we can define Now, if these two are analytic manifolds with corner, an element that lives here is basically something that lives in a slightly bigger, so it's something that is a current in the product that can be enlarged to a, so I can embed this in a slightly bigger manifold, as an analytic manifold of the same dimension as the product. And in this manifold, there is this current TU, which is closed, and well, it's an enlargement of V and W. I can enlarge them in such a way that all those properties hold, and then I restrict the manifold with corners. So in other words, essentially, I can enlarge both U and W in this form, which is a V hat plus W. They no longer have corners.
So you embed them in a regular manifold, so to speak.
Yes, a manifold without, so it's a restriction of something that comes in a slightly bigger manifold. But in particular, this condition is no longer true, but the boundary of the current will be precisely restricted to the boundary of the manifold with corners, lie above it. So I can make this enlargement without lack of, without losing anything, but it will be important for us to make that extension. And now I'm going to do something that the algebraic geometers will recognize this, and is that I'll try to compose those objects. And so the picture is the same that you do with correspondences, algebraic geometric correspondences. And the proposition is that so if you have V, W, Z elements here, because we could have corner, and then of course this has dimension V, W, little z, and then I'll denote maybe this thing W hat W, which is by definition V cross the diagonal of W cross Z containing V cross W cross W cross Z. So, so now suppose that I have something that I'll call here that belongs to this analytic finite correspondences from V to W. I have something that belongs here from W to Z. So I think about Z as a correspondence here, T here, and my S lives here. And now I can take the cross part of them. And so then, the intersection now, of course, that you say, well, there's not a good intersection theory for currents, true, but for these type of currents, you can define some type of slicing locally that allows you to, in some cases, define this intersection in the appropriate way. But this intersection exists. Okay, so there I can the idea is that I take this product here, and then I can intersect at the diagonal, and this is still a well-defined integral current, which is a well-defined analytic object.
Normally in geometry, we just look at V cross W cross Z. So and we just do pullbacks, and then you just did this.
Well, so the point
I mean,
is
it's the same thing, but I just
the point is that to define intersection currents, usually you work locally on the product, and then you look at locally if these are common sets in Euclidean space, you have to map them to a certain ball in Euclidean space, taking the difference of their. In other words, the idea is that I take coordinates Z and T, and I send to Z minus T, and use this map to do a slicing, which exists almost everywhere in geometric measure theory. And then under this circumstance, we can show that it does exist everywhere, and so that's why we're actually doing it in this form. But it's just a way of writing it down. And now, of course, that if you have P, which is a map from V cross W cross Z, and I send to V cross Z is the projection, then implies that the restriction of P to the support of the intersection is proper. So in particular, I can push it forward. I can push currents forward, and if it's an integral current, the push forward is still going to be such a piece. And then the current, when I send down the push forward of this current, belongs to this same object. So of course that and so in particular I would define, so I can define, and there's not, I'm doing nothing original here from the sort of from the broad scheme of things, especially if you know the work of Blavatsky. But on the other hand, from the differential geometric standpoint, this is something that can have interesting applications that we shall see soon. But also I want to give a topological motivation for what I'm going to do in the algebraic geometric context. So in particular, I can define simply S composed with T to be precisely this projection over here. And so, and then some properties. One is that if I, whenever this makes sense to compose in this form, ST gamma is equal to S composed with T composed with gamma. And then also, if I have, if S is the graph of analytic map and T is the graph of another analytic map, then this implies that this will be exactly equal to the graph of the composition. So, particularly, this generalizes the composition of functions as one would expect. And so this can define, I can actually define another category now, I'll call, is the category of analytic manifolds, but I now put a little fin for finite. So this is the objects of this category. It's a category with objects equal to this oriented analytic manifolds with corner oriented manifold with corner as before, the same objects as the previous category, but with morphisms, let us see, the morphisms in this category between two such things will be precisely these currents. Okay, that's a category. And then I will just mimic what comes later. So I can define a topological or analytic, if you want, pre-Shively transfer is, let me put the letter F here, is a contravariant functor F from this category. The categories are big groups. So to be contravariant, I will put the opposite category. That's it. So it's something that, so examples, of course, that, so examples, if I pick an object, let's say M, is an object, is an analytic manifold, then you define, let me put a Z, I'll put the W for analytic, real analytic, TR for transfer M, is the functor represented by M. So in other words, it sends, this belongs to, and let me put this, let's call this PST with a little w for analytic. And so this is something that belongs to PSTW, and the idea is that as a functor, it sends any analytic manifold with corner to the group of finite topological correspondences between U and M. This is an abelian group, and this is a contravariant functor that we shift with transfers. All right, so now, this is the representative functor. Let me just tell one thing that I'm just doing this in order to do a few things faster and also to motivate what comes next. So let me give you some examples. So, let's have notation first. So I'll put a delta, and I'll do it a bit dark, delta n. It's just the canonical topological simplex, right? So it's just the T0, the n, sum of the Ti is 1, and Ti is topological simplex. And of course, this is a typical example of an object that lives here, right? It's an analytic manifold. And is an object in this category. And it's formed a standard, I can put like this is the standard for simplicial object. So we have faces and degeneracies that make this into a co-simplicial object. So given this, then, so given any f, a functor of that type, so we can define delta dark n of f, again a functor in the same category, by sending a manifold here to the value of f in this manifold cross this dark simplex. Okay, so in particular, therefore, we get, since now this is contravariant on this part, it becomes contravariant on the delta n's, and therefore this introduces a complex of PSWs, which is the complex that we denote now delta singular F. Okay, because this assignment becomes a simplicial resheaf, and then you can always associate the simplicial abelian object is chain complex. So, and I want to see this also as something graded in negative degrees as I've done before. So it's always cohomological complexes. And the last ingredient that I'm going to introduce is the following. And now everything's going to converge at this point. So now let's introduce the notion of the smash product in this category. Suppose I have two. So suppose I have v and a base point x naught. I have w and a base point y naught. And I want to define z of v smash w as again an element here by, well, this is essentially how you would define. I want you to think of this as the free abelian group on the wedge of three spaces. Remember, we started the first lecture on free abelian groups on spheres as representing algebraic McLean spaces. Now I'm generalizing that to this context, and so, but now this is a pre-sheaf. So this is a functor that sends a analytic manifold U to the following. I send to Z the transfers. First I take their product and I apply it to U. But now I look at a subgroup of those. Remember that these are correspondences that are contained, right? That are contained in U cross V cross W, right? And now I want correspondences that are contained in U cross a point cross W or U cross a point here cross V to be 0. So then mod the image, right, of that I have Z transferred of V cross Y naught applied to U, direct sum with all those of X naught cross W of U into the thing above. So there's a canonical map from this, the inclusion of this in here, the inclusion of this in here. I can include the correspondences, so that includes a Z transfer. I urge you to make an exercise of making U into a point and see that this essentially sort of coincide with the free smash product of the MW in some way. So I define that. In particular, I can iterate this construction several times. So can define Z transferred W, say the same space smashed with itself certain number of times, p times. So just iterate with m and m and m and m several times. Right? In particular, if I had a circle S1, I could do that, and that would somehow now, so here's where the interesting part comes. So philosophically, and later on we'll do that more precisely. There's not only philosophy going on here. You can have a circle S1 and set it to C star. And this is actually, I can have an equivariant deformation retract under the Galois group. From the point of view of Z2 equivalent homotopy theory, these two are the same. Again, the deformation retraction that you learn in high school onto this is equivalent with respect to the Galois group action. And so, in principle then, I could, well, I know that I want to equate this in some homotopy theoretic sense with this, okay? So now I will do this in this particular context over here. And of course, we learned that this is the same as your SP. So the p-fold smash of C star, in some senses, equivalently, similar to this, to SP over here. Now, I'm gonna, oops, it's alive. Define my main object here, and I will do what the algebraic geometers do. And so I'll define I'll define a complex, so fix p greater or equal than 0. Okay, and I'll define the following complex, Zp, and I'll put a b here, and the b will stand both for Betti, which means similar cohomology, or for Bredon, when you're doing ordinary equivariant cohomology. I'll treat both at the same time. So I'm one for the Galois group of C over R. Z2 equivalently. And the way I'm going to define this is the following. I will look at this Z-weight transfer of the sphere S1, but now I want to be C star, smashed with itself P times. So this is just this pre-Shiva transfer here, several times. But now I will look at this singular complex associated to it, the complex of sheaves. But now, remember, this is greater in negative degree, and now I want to shift it minus P. So I'm shifting it to the right. Okay? And so I'm defining this object, and this is essentially an Allenberg Michael space. So now let's go back and let's first go back to so now go back to the category of manifolds, and then I will jump all the way back to spaces in the following way. So we know that manifold, there is an embedding of this in this other category with the morphisms. This has more morphisms than this one. Right? This has all the correspondences, where this are just the functions that I send a manifold to itself. Objects is the identity, and send a function to its graph. And now if I have a pre-Shiva transfer, implies that if F is a PST, so if F belongs to PSTW, implies that I can restrict F to this category and becomes a pre-sheaf on this category. I can actually shift it, and this is actually a site. Here, or if I have or in G manifold, whereby this is the same thing, but I put an action of the group in everything I've been doing so far. So everything I've done can be done equivariantly. So now the currents have to be invariant under the action of the Galois group. It's fixed by it. But that's the same thing to say that the map is an equivariant map. Right, so now this becomes a pre-shift on that. These both are sites. I'm not going to go into that with details, but I can always shiftify them. And so the goal is that now, so we will do homological algebra, or homotopical equivalence, homological algebra, with like this, in the category in sheaves on, let's just write like this, sheaves double. If this is equal to 1 billion sheaves on this. So, so remember the idea is that we have spaces, you can put spaces in this other category and then do homological over there, and I retrieve back single homology. So now I have actually the complexes of sheaves. Okay. I'm really doing complexes that are bound at the bottom of sheaves on this manifold. So the theorem that now I'm going to explain is that suppose, okay, so given a manifold, an analytic manifold, then I have to potentially define. So then the hypercohomology, so James explained what hypercohomology is, and I open either here or a G manifold where I have the action of the Galois group of X, and then here I could put either the analytic topology or the equivariant site, so I see there's an object in action. Of this, I can look at this sheafified, and I restrict to X, so this now becomes, so in other words, I'm only applying this, this object to the open sets of X, or the open sets with the action, and like I take the hypercohomology of that, and this is canonically isomorphic to singular cohomology in X.
Singular?
Oh, this is Becky.
Okay.
But if in the non-equivariant case, if I do an equivariant site, this will be precisely what I call Hn comma P of equivariant of X with coefficients in the Matic-Funke Z lenses. I explained these two objects in the previous two lectures, but now I was careful. These two things are isomorphic, but as a matter of fact, I'll even explain. I will tell a little bit the sketch of the proof, but I'll give you instead also an explanation why it is better to think actually this is more. And my more precise statement of that is that this, more precisely, so I will give you a realization of the inclusion of this is Betti singular cohomology with coefficients in ZP, where ZP is the 2 pi I to the P times Z inside this. So inside the complex cohomology.
I was going to ask about, were you intending to put ZP just right away, or?
Yeah, after that explanation, yes. Well, that's why I have an isomorphism here.
Yes.
But it's more naturally I would put this, and I would like to have this.
Yeah.
But mas albismo parece igual. So the point is that this is compatible. If I put the action of the Galois group, for example, this has an action of Z mod 2, then the isomorphism becomes equivariant. If I put, if I make the simultaneous action here and pull it back here.
Yeah, I'm a little, for any space, but if you have and suppose X is an algebraic variety, okay?
I'm gonna get that in a minute.
I was just wondering how you would define a Galois action in the Betti case.
In here, well, it has to be a algebraic variety over R.
Right.
You look at the complex.
Yeah, okay, gotcha.
You have, the idea is that I'm seeing real varieties as a pair. You look at it as a complex variety with the action of the Galois, anti-holomorphic action of the Galois.
That makes sense. And that's continuous, that one.
Yeah, absolutely.
All right.
Yeah.
Well,
No, so, and that's the way, this descent philosophy that.
Gotcha, okay, so I understand that.
So what's X cubed?
Well, okay, X could be either a manifold or a manifold with action Z mod 2. Say again? I have either this or that. And then without the action, I get single cohomology. With the action, I get this Bourdon cohomology. Right. And so now let me see. I want to realize this. Actually, I'm going to give you a map of complexes. So giving map of complexes. When I take this Bourdon, I restrict to X to the complex of all the run currents on X. The run currents. Okay, and so how do I give such a map? Let's call it actually how of X, right? And the idea is the following. Suppose that you have, if you have U is an open set containing X, and then of course in the equivalent case an open equivalent set, then an element, say alpha, that belongs to what you call ZP upper J beta of U. What is that? Right, this thing is a quotient, because if you unravel all these definitions, there is a shift by minus P over here that must take place. Then you have to realize that this is represented, is the class of a current. Why do I say class? Because to define this smash current, I have to divide by the horizontal ones, the ones that live in one. Right, so I'm thinking about C star as a based object at 1. So anything that's horizontal living in 1 dies. But let me, where T, if alpha is in here, it's represented by T, where T belongs now to these finite correspondences from U cross. Here this is going to be delta P minus J. There is this J up here becomes minus J because of the shift. Cross C star to the P. So this current, the support maps onto this properly. Okay, this current maps properly over here with finite fibers. And so now, there are two ways. If you are, and so let's call this projection pi, projection to this. If you are, but let me tell. On the other hand, I have a map from these into C star to the P. And so let's call this pi 1, let's call this pi 2. And the idea is that I want to produce a current. So I want to send this, I want to send it into a J current on U, which is the dual. Let's suppose the dimension of X is equal to, say, N. So this is the dual of the differential forms with compact support, the N minus J supported on U. Right, so then let's pick a form that lives here. Pick a form that lives there. So I'll put the definition at what it means. You define how to call tau x alpha to be the current which is represented by, you take the push forward of a current, push forward of the current which is T smash with pi 2 pull back with the current omega p, where omega p is d log, say, z1 smash d log zp, which is a current that belongs to, actually, and this don't forget that this is 0 in every slice. Therefore, it allows go to the quotient. So, in other words, this current here, so this current, let's call it, is still tau x of t. The idea is that if I do tau x of t applied to the test form over here, this is simply by, I take the pullback of the test form, I smash with the pullback of the form omega p, and then I integrate that over, check the dimensions, it all works. And then the usual formulas for raising the boundary of this with restriction to the faces of the simplex guarantees that this is indeed a map of complexes. The map of complexes for here. What's nice is that somehow, if you pick a cycle in this business and you integrate over this, you end up having two coefficients, periods in ZP. Right, so, because I'm not dividing this by 1 over 2 pi to the p. So this is very natural. It's independent of any choices or square root of -1.
Boy, I really like that. So that W omega p creates the twist. That's fun.
Completely natural. And so eventually I'm going to use this map of complexes also to, I can use this as a model of Z, and I can use that to define this Billion cohomology. Right? I pick a piece of the filtration in here, add with this, and take the cone of the difference of the maps. So that's a natural way of constructing the Billion cohomology, both in the complex and in the real situation, the same map. This is a map, and this map respects the action of the Galois group as well. If the action of Z mod 2, if this is a manifolded in action. So this is compatible with that action. Where the action here is taken pullback and conjugated. Okay, so now I defined a. So now there's only one question that I would like to just hint a little bit. So this is the last remark I'm going to do before in the last 10 minutes, I introduced motivic complexes of Blavatsky. But basically the idea is that these complexes, they do represent singular cohomology. And I will tell you a little bit how, I can give an idea of the proof, but the proof is simply given by the inclusion of S1 into C star. It shows that is a homotopic, is a quasi-isomorphism of complexes. If I replace C star by S1, and then our S1 is compact, there's a nice way of saying each correspondences to maps into the free abelian group on S1. And then we are back to my first lecture. And all together, you show that these are complexes of sheaves with, or pre-sheaves with homotopy invariant cohomology sheaves. And that's makes everything reduced down to a point. But I won't say any details unless you ask me at the end. But now, what about single homology for any space? So there's a remark. I said that I can send the category of topological spaces into the category of let's say, sheaves on this manifold, simply by I send X to the, let me put like Z, let's say Z like this, X, whereby this is an element that sends a manifold to simply the continuous maps from U to the manifold. And then I take the free abelian group on that. So I send this into that, and now here, of course, then I can send that into the category of complexes, of sheaves on this, bounded. Now this, I have its associated derived category, that I'll just call D, whatever, min, nega, minus. The derived category of bounded sheaves of complexes and so on. And as an exercise, at least if X is nice enough, let's say X is CW complex, could be just something that's locally homologically connected, blah, blah, blah. Then the single homology of X with coefficients in Z is just hom in the derived category between this and Z in the shifted. Sounds familiar? I mean, I said before, in my first lecture I said, you create a single complex of X, then you look at Z and you shift Z by N, and you look at homotopy class of maps of complexes between the single complex and this, and you get single cohomology. So I did that the homotopy class of maps in the derived category of complexes of abelian groups to get single cohomology. I just changed a little bit and made it much more complicated for reasons that are not completely clear yet. I could realize single cohomologies are a complex. What's nice is that in the equivariant setting, then I can put this in a P, and I can put a group here, and I can do the Marquis-Funter, and then of course I have to put the action of the group here, and everything remains the same. And so that's the only advantage of doing that, because I want to incorporate the action of the Galois group. So now, this, my fingers will become more and more. I won't go into the proof, but now let me start with a complete change of gears. And let's go and explain very quickly, because I don't have much time. Now let's go to motivic complexes. But now I'm going to go really quickly because it's going to be all an exercise for all. So here fix.
Just give.
Oh, forget that. Fix a field K. Eventually, we're going to want the field to be perfect. Fix a field K. Then denote by the smooth of the K is the category of the smooth schemes. And by smooth is separated always over K. Okay. So now I will define so if you have two such schemes, define the finite correspondences. I just denote like this, and like the finite correspondences. I believe for this audience it's simpler. This is just correspondences that is in the space of cycles of dimension n, which n is the dimension of x, inside of x plus y, such that if I have such a cycle, over here, then T is a sum of ni, vi irreducible, such that the projection x restricted to vi is proper and surjects, that's not proper, it's finite. Well, finite in the sense of algebraic geometry, so it's proper with and quasi-finite. It's finite and surjects onto some component. Of. So this is an abelian group. There's a free abelian group on some subvarieties of x cross y. And the claim is that
What is n dimension?
so n is the dimension of x. It's the dimension of this. So then there's a lemma. And now you look at the So if I have T and S, T belong to this correspondence of V, let's say, well, I can do the same letters, V and W. S belong to this finite correspondence of W and Z. Then you can define, so let's say T is what? S composed with T. S, something like you take phi 1, 3, push forward of what do you take? Phi 1, pull back of whatever, so T intersecting with pi 3 pull back of S, where I have here V cross W, cross Z, and I have the obvious projections.
So the third one is P begins with one P1.
Okay, so let's say, or maybe this is, okay, you're correct. This is pi 1, 2 with V cross W. This is pi 2, 3. This is into W cross Z. So this should be pi 1, 2 of this, and this should be pi 2, 3 of this, and then this should be pi 3. I think now it's right. So if you do this, then, in other words, these two cycles, they meet properly, they intersect. The intersection is still projects finitely over V, and this is basic stuff in intersection theory of algebraic cycles. And S composed with T, composed with gamma is equal to S. So in other words, you can define for sub K to be equal to the category of finite correspondences. Which means it's the category that has as objects smooth varieties over K, and where the morphisms are precisely those correspondences of this type, and that's the composition. And obviously, if I have a map from V to W, look at its graph. Also, it's nice that if you have a finite map from V to W, you can look at its finite surjective, you can look at its graph, and then transpose, and there's still an element in this category. So that's why I call it. And now that comes with the definition that all this is now taken from Voevodsky, Weibel, Mazza book. You've seen Weibel, Blackman, these ad infinitum. So I'm really not doing anything new, but I hope I've been at least adding the topological perspective of why you do things in this way. So, and therefore, you can define a PST over K, which is a pre-Schiffer transfer F, is a contravariant functor F from the category of finite correspondences to Abelian groups. So an example is, if you have Zx, then you can define Z transfer of X applied to U is just the correspondences from U to X as before, and this is the pre-Schiff with transfer represented by X, and everything I've done before applies verbatim. It should actually be the opposite, but I should start with this and go back to the other. So now we have a standard co-sequential object that James used to define Bloch-Hatchall groups. Now I'm doing like this, not dark anymore. So this delta n is the spec of K T0 Tn mod the ideal generated by T0 plus Tn minus 1. And this forms a co-sequential object, so there's just an affine plane of dimension n over the field. You define the mesh product in the same way I defined before. I wouldn't know for the topological case. I wouldn't go there. and then I will define ZP M motivic as a complex. This is going to be a complex of PSTs. As by definition, well, I start with GM, and I think of this as the pointed scheme, where this is the affine line minus 0, which is our C star in the previous case, and pointed by 1. This is a pointed object. I can take smash of those things. So I will take the element represented by that smash. I smash it with itself. Let me just write like this. I smash with itself p times. And now I take the complex associated to that co-simplicial object, and I shift by minus 2. One fact is that if you pick a smooth scheme over K, then the restriction of this to X is a Zariski, the complex of Zariski sheaves. Definition: motivic cohomology of X with coefficients. That's not the notation of Blavatsky, but it's the one that everybody loves. This is just the hypercohomology N of X in the Zariski topology with respect to this complex of Zariski sheaves. For any field K,
Is this really Zariski, or are you talking on
Zariski topology. So it becomes, it's the same as if you take a Disnevich topology.
I see.
Okay, so the point is that here, I'm not talking about the triangulated category, right? So when I want to go to the derived category of motive, the triangulator, and then I have to use the Disnevich topology. But this hypercohomology does not change. Okay, so the point is that, yeah, that's not going to the one moment of the subtleties, but I can define using Zariski right away. And not only that, so examples.
You don't need suffix n in the second sign?
I'm sorry?
You don't need suffix n in this complex. ZPM is ZP or ZPM? CP.
No, this is Zariski cohomology. I'm not taking the derived. So if I want to go to the derived category, then this is a morphism in the derived category of the Zariski, the shift represented by this, to the shift of this by m, but that's reflected here. That's reflected there. Okay, so anyway, so my time is up. If you give me 2 more minutes, I'll just say a few things that are relevant. So one thing is that this is quasi-isomorphic to the sheaf obtained by look at the units and shift by -1, and therefore, for example, H2 motivic X Z1 is just a Picard group, for example, and then H11 is just the units on X and the verbal functions. Let's say 2, and this is an important result. When the field K is perfect, if K is a perfect field, if K is perfect, then
Paulo,
yes.
in the first point, one P to be equal to 1.
Yeah. Oh yes, yeah. That put P now. This is 1. This is 1. So when P is equal to 1, otherwise that we know theory. Thank you. Now, if K is perfect, then this nth cohomology of X with coefficients in Z is isomorphic to the block higher Chow groups P that I'm going to do this right, 2p minus n.
Yeah.
So, in other words, the higher tau groups that James mentioned also is isomorphic to these in this case, in particular when k is equal to r, when k is equal to the complex number. And not only that, so the whole reason I've done all this was to end by, suppose now that you have either a real or a complex smooth variety. So an example of the cycle map is that suppose you have x defined over R or C. Let me do the C case here and let you figure out the R case. So you can think about X with a analytic topology, so as a smooth complex manifold, and there's a continuous map from this into X with this Zariski topology, correct? And I have this complex of sheaves that I had before here, ZP Betty restricted to X analytic is a complex of sheaves on this space. I can push it forward. I can push forward this complex of sheaves to get a sheaf over here. And in fact, I can then very naturally describe, I can actually describe a map from ZP motivic restricted to X straight here, which then which can be used eventually to give you a map from the ZP. Anyway, yeah. Well, and that gives you a map from the hypercohomology. I'm skipping some little things here, but gives a map from the motivic cohomology of X with coefficients in ZP down to the singular cohomology, because it induces a map of the hypercohomology groups. This is now the analytic topology. So this is Zariski for the analytic. And what the map is, simply if you look at the correspondence, which is an algebraic correspondence, then you just look at that as an analytic, complex analytic cycle, which is in particular a real analytic cycle, and you see that as an object in the complex that I defined before. It's completely natural. So that's it.
Well, I can ask a question.
Sure.
There is a construction block using essentially Golden type resolution and so on that, and invariance and homotopy to construct a map from the higher child groups into any good homology theory. I'd be willing to bet that isomorphism is induced by that construction.
Oh, I probably can bet.
In which case, the other way should also work since Kotbowski's is analytic promoting cohomology.
Yes.
And that way-
So one thing that, what I think is very natural and ties with what we do in topology for ages. Right? And I think in some way that what inspired a lot of the construction of Kotbowski in developing some homotopy theory. And another thing that I like, is that embedded in this isomorphism, this is a pretty difficult isomorphism, right? It does have already some sort of moving lemma proved by Suslin that allows you to express this in terms of some sort of a complex of equidimensional cycles after you do something to it. So, and not only that, this thing has essentially a covariant character. And it's hard to prove contravariance of this. It requires some hard work to show that this is contravariant on X for X is smooth. And so, whereas this is completely natural, and naturally it's completely contravariant, and maps of this type, for example, can be very easily described by what's embedded here is just picking a scheme over complex numbers, and then look at the complex points in analytic topology, and that's a function from schemes to topological spaces that transcends and becomes a map of Quillen, as a Quillen map between two model categories in homotopy theory. And so in that Quillen map is what sends one theory directly into the other, sends algebraic K-theory to topological K-theory. And in the equivalent case, sends algebraic K-theory into Attia's KR theory, and sends motivic homology of the real numbers. If I had the real numbers, this would be motivic homology, and here would be the Breton H and P that I described before. So it's very natural in that sense. It respects the whole homotopy structure that is model category that we have in the one homotopy theories and in classical equivalent homotopy theories. All right.
Any other questions? Okay, let's thank you.
I just remember that the talks are going to be